In this lecture, the second of our series on valence and the electronic structure of atoms, molecules, and crystals, I shall talk about the covalent bond and the shared electron pair bond. They are the same thing, two different names. The covalent bond, covalence is an aspect of valence that I think comes closer to the old-fashioned, rather vague concept of valence than do the other more precise aspects of valence that we make use of at the present time. The theory of structural chemistry involving the idea of the covalent bond represented by a line drawn between two symbols, the symbols for two atoms. This theory is one of the greatest constructs of the human mind that has ever been formulated, perhaps the greatest of all. The theory of structural chemistry was developed about 100 years ago. It was in 1852 that Franklin suggested that different elements have different combining powers, can combine with different numbers of atoms of other elements. In 1858, Kepler and Kekulé invented the idea of the chemical bond and discovered the quadrivalence of carbon. Then there was great progress in chemistry with the aid of this relatively simple theory that had been obtained by induction from the many thousands of facts of chemistry. It was possible for chemists to make the extraordinary progress that has led to modern technology and medicine. The structure theory assisted the imagination of a man in such a way that he was able to make discoveries that would not have been made otherwise. I should like to start out by talking about the simple structure theory, the simple idea of the chemical bond in the substances that we now consider to contain covalent bonds. As an example, I may take methane, represented by this model, a carbon atom with 4 hydrogen atoms attached. We write for this the formula CH, H, H, H. And, of course, Kepler and Kekulé recognized that the carbon atoms forming 4 bonds can also be attached to one another. I have another model here representing the structure of ethane, the next hydrocarbon in the aliphatic series. C2H6, 2 carbon atoms attached together, 6 hydrogen atoms. Each carbon atom is quadrivalent, forms 4 bonds, 1 with the other carbon atom, and 3 with the 3 hydrogen atoms that in the structural formula are shown connected to it by the valence bonds. As a more complicated example, I may show ethanol, ethyl alcohol. Here we have the 2 carbon atoms bonded together, 3 hydrogen atoms, 2 here, a bond to the oxygen atom, and then a bond to the hydrogen atom on oxygen. C2H5OH, ethanol. I may mention that these ball and stick models are quite illuminating, but they do not give a really correct idea of the shape of the molecule. The ethanol molecule does not have a thin portion that connects the carbon atom to the hydrogen atom. Instead, the electron distribution in space is more satisfactorily represented by this model, a space-filling model, in which the atoms are shown as spheres with a radius that corresponds approximately to the effective contact radius when the molecules are piled together in a liquid or in a crystal. If there were another molecule in solution, say, in ethanol, for example, this rather larger molecule, then the molecules would roll over one another in such a way that they would not get much closer to one another than the distance corresponding to contact between the spheres that represent the atoms in these models. I shall continue to use, in general, these large models. You must remember that they do not satisfactorily represent the extension in space of the substances. A very important contribution to structure theory was made in 1874 by the Dutch chemist Van 't Hoff and the French chemist Lebel, independently of one another. This is the idea that the four bonds formed by the carbon atom are not directed out toward the corners of a square in one plane, as indicated here on the blackboard, or are not so loose-jointed that they have no well-defined direction, but instead are directed toward the four corners of a tetrahedron. All of our models are built in this way. Here we have the methane molecule with the four bonds shown proceeding toward four corners of a tetrahedron, a regular tetrahedron. It has been found in recent years by the determination of the structure of crystals and of gas molecules, by the X-ray diffraction method, the electron diffraction method, and various spectroscopic methods, that the angles between single bonds formed by a carbon atom remain in all substances quite close to the tetrahedral angle, the angle for a regular tetrahedron, 109 degrees 28 minutes. The tetrahedral carbon atom is a very important part of chemistry. I think that the discovery of the tetrahedral carbon atom was a wonderful thing. It shows the power of man's mind. The facts were that in 1874 it was known, as a result of the work of Pasteur, that some substances can form crystals that have either a left-handed appearance or a right-handed appearance. Van 't Hoff and Lebel asked, how is it possible for substances to be built up of molecules that are right-handed or left-handed, two different kinds of molecules that are related to one another in the way that the right hand and the left hand are related? They showed that the tetrahedral carbon atom provides the explanation of these facts. If the four bonds of the carbon atom are connected to four different kinds of atoms or groups, for example, a hydrogen atom, a methyl group CH3, a chlorine atom, a bromine atom, then this tetrahedral molecule can be either a right-handed molecule or a left-handed molecule, and the right-handed molecule does not become left-handed by any translational or rotational motion in space. Only by breaking the bond and moving it around to the other side can you convert the right-handed molecule into the left-handed molecule. Recent investigations, recent structure determinations have, of course, completely verified this idea of the tetrahedral carbon atom. The simple chemical structure theory permits one to understand the existence of isomers. I have here a model. Let me start with this one. I have here a model representing one of the two forms of butane, C4H10, 3, 6, 7, 8, 9, 10. C4H10. This is normal butane, a straight chain hydrocarbon. It is called a straight chain, even though the bonds are at the tetrahedral angle here, so that the chain is a zigzag chain. Normal butane is one substance. There is another substance with formula C4H10 that has somewhat different properties. This other substance, called isobutane, is represented by this model. Here we have again four carbon atoms and 3, 6, 9, 10 hydrogen atoms. But the bonding between atoms is different for isobutane from that for normal butane. These are the only two ways in which 4 carbon atoms and 10 hydrogen atoms can be attached together, with each carbon atom forming 4 bonds, each hydrogen atom 1. And corresponding to this, there are only 2 isomers known, 2 substances known that have the composition C4H10. This provides an interesting, simple example of the power of chemical structure theory. Now, there are many other sorts of molecules that one can build that are compatible with the simple principles of structure theory. I have here a model of a new sort in which there is a ring, a cycle of carbon atoms. This molecule is the molecule of cyclopentane, C5H10. The angle in a pentagon is 108 degrees, so very close to the tetrahedral angle, so that there is practically no strain in this molecule. On the other hand, a smaller ring involves some strain. No longer are we able to use half-inch wood dowel rods in representing the bonds. We have to have springs in this model, which represents cyclopropane, C3H6. Here we have bent bonds connecting the carbon atoms. If the bonds came directly from carbon atom to carbon atom, the angle would be 60 degrees instead of the tetrahedral angle, 109 degrees 28 minutes. We can represent the structure by the use of these bent bonds. There is some strain associated with the bent bonds, so that cyclopropane is somewhat less stable than one would expect for a molecule with the same composition and without the bent bonds. It is interesting that this substance, cyclopropane, is used as a general anesthetic. It produces anesthesia. I think that this is an illustration of the present situation in physiology, biochemistry, our lack of understanding of the nature of the human body. Why is it that this particular molecule produces anesthesia? Why is it that chloroform, CHCl3, produces anesthesia? Nobody really knows the answer. No one is able to predict what substances will be anesthetics and what not. Here we have chloroform with a hydrogen atom down here. I'll hide this chlorine atom to make it into chloroform. No one knows why chloroform serves as an anesthetic, too. Some light on this question is provided by the fact that xenon is also a general anesthetic. Now, xenon is one of the noble gases, atomic number 54. It forms no chemical compounds in which it forms chemical bonds. It will, in fact, form a hydrate, xenon hydrate, in which the water molecules are arranged together, attached to one another in such a way as to make cages, little rooms, in which the xenon atoms sit. It is interesting that cyclopropane forms a similar hydrate, and chloroform forms a similar hydrate. In the case of chloroform, the hydrate is something like CHCl3 17H2O. I think that it may well be that the effect of these substances in producing general anesthesia is related to their power to form moderately stable hydrates, stable at temperatures 10 degrees or more above the freezing point of water. Perhaps somewhere in the tissues in the nervous system there are little regions where the water is tied down into a sort of pseudo-crystalline aggregate by the molecules of the general anesthetic, and the normal metabolic activities of the nervous system are not able then to go on. But we really don't know enough about the chemistry of the human body to be able to give an explanation of this. Well, let me go on to discuss some things that we do know about. This model This model represents the structure of ethylene. It has something new in it, a new structural feature. Here we have two bonds connecting one carbon atom with another carbon atom, a double bond represented in the conventional way by two lines between the carbon atoms. Ethylene is an interesting substance. It causes oranges to ripen. If you have oranges that aren't very ripe, look sort of yellow in a freight car, and put some ethylene into the freight car, the oranges develop a beautiful orange color. Nobody knows why that goes on either. Well, here is the double bond. We can say two bent bonds holding the two carbon atoms together. Now, if this double bond is described as involving two tetrahedra that are attached together with one edge in common, then we can see that there is restriction in the rotation. It is not possible to twist the molecule around through one end through 180 degrees relative to the other end. To do that, one would have to break a bond, and this takes a lot of energy. The result of this is that a new sort of isomer is found in substituted ethylenes. If we replace one of the hydrogen atoms on this end of the molecule with, say, a chlorine atom, and one on the other end with a chlorine atom, we may do this in either one of two ways. This hydrogen and this hydrogen may be replaced by chlorine. That gives one substance. Or this hydrogen and the opposite hydrogen may be replaced. That gives another substance. These substances have different properties, different chemical and physical properties. They are represented by the models shown here. This is called cis dichloroethylene, in which the two chlorine atoms are on the same side of the double bond. This molecule, represented by this model, is called trans dichloroethylene, in which the two chlorine atoms are on opposite sides of the double bond. Well, here again, we have only two isomers with the formula C2H2Cl2 and with the chlorine atoms on separate carbon atoms. There is also a third isomer in which there are two hydrogen atoms attached to one carbon atom, two chlorine atoms attached to the other carbon atom. In addition to the double bond, the triple bond is known. There are substances such as acetylene that contain a carbon-carbon triple bond. Here we have three bent bonds holding the two carbon atoms together. The other two bonds project out in opposite directions. The molecule acetylene, C2H2, is a linear molecule. The conventional representation of this molecule is CH. No quadruple bond is known. Nobody has ever recognized the quadruple bond, at least so far as I am aware. In reading the chemical literature, I have never seen mention of evidence that a quadruple bond exists. Perhaps we can understand that, too, in terms of the tetrahedral carbon atom. For carbon, at any rate, the four bonds come out in these directions. We can have a double bond by bending the bonds, triple bond by sharing two faces of the two tetrahedra and bending the bonds out enough. But the fourth bond would have to make a terrific bend in order to get around from the backside of this carbon atom to the backside of the other carbon atom. Now let us discuss the modern aspects of valence theory, structure theory. First, let me say that the classical structure theory, the older structure theory, has not been discarded. There has not been a revolution of such a nature that the old has been thrown out and the new has come in. Classical structure theory is still valid. There have been some improvements in structure theory. Some problems of molecular structure and valence that were hard to discuss, hard to understand before, can now be discussed in a reasonable and sensible way because of the additions that have been made. Ideas about hybridized bond orbitals, about the theory of resonance, partial ionic character of covalent bonds have come in and have made chemical structure theory more powerful. The whole theory, the classical structure theory and the modern structure theory, has a sound base in experiment. It has been developed largely by induction from the tens of thousands of chemical facts, with, in the case of the modern development, a little help, or considerable help, I should say, from ideas that have been suggested by the theory of quantum mechanics, for which we are indebted to the physicists. The modern theory began in 1916 when Professor Lewis introduced the idea of the shared electron pair chemical bond. And much contribution was made also by Irving Langmuir. The principal statements that we can make about a chemical bond now are that in order to form a chemical bond between two atoms, you need to have an orbital for each atom. Let's say atom A must have an orbital, atom B must have an orbital, and two electrons are involved, which I may write in this way, and their spins must be opposed. One orbital for each of the two atoms, and a pair of electrons with opposed spins, which serve to hold the atoms together. Here I have a drawing representing the structure of the hydrogen molecule, H2. The two nuclei, the two protons, are at these positions, 74/100ths of an angstrom apart, and the two electrons are distributed in space, roughly as shown here, with a good concentration right in the region between the two nuclei. It is almost as though the nuclei were ball bearings, say steel ball bearings, around which some rubber has been vulcanized that holds these ball bearings firmly at this distance apart, does not permit them to escape from one another. This is the standard Lewis symbol for the hydrogen molecule H2. The two electrons are shown between the symbols for the two hydrogen atoms. We see that we can say that each of the hydrogen atoms has succeeded in obtaining the helium structure. This orbital for hydrogen, the 1s orbital, is occupied by the pair of electrons, which also occupies the 1s orbital for the other hydrogen atom. The idea that you must have a stable orbital for each atom in order to form a bond and a pair of electrons permits a considerable addition to the power of chemical structure theory. Here I have a drawing representing the electronic structure of the water molecule. The water molecule, H2O, has the Lewis symbol as shown here. The pair of electrons in the helium shell for oxygen is not indicated, only those in the neon shell. Here is an unshared pair of electrons occupying one orbital, a second unshared pair occupying a second orbital, a third shared pair, in this case occupying the third orbital, and a shared pair occupying the fourth orbital. The oxygen atom now has 4 electron pairs, 8 electrons in its neon shell. It has achieved the structure of the neon atom by sharing electrons. And the hydrogen atoms, as before, using their 1s orbitals, have achieved the helium configuration. Many structures, many molecules have structures such that each atom achieves the electronic structure of the nearest noble gas with 2, 10, 18, 36, 54, and so on electrons. The oxygen-hydrogen distance is known, 0.965 angstroms. The angle between the two OH bonds is known experimentally, 104 degrees, 30 minutes. These distances are interesting in that the distances as determined by spectroscopic or diffraction measurements, in that they give us an idea about the significance of the chemical bond. The carbon-carbon distance, let me look at this. The chlorine-chlorine distance in the chlorine molecule, Cl2, is 1.98 angstrom. We can write the Lewis formula, Cl. And I shall show also the electrons in the valence shell, the argon shell, of each chlorine atom. I have written here a line like this to represent the two electrons that are shared between the chlorine atoms. Chlorine has only 17 electrons, that is 7 in the argon shell. But by sharing a pair, each chlorine atom succeeds in achieving the argon structure with 18 electrons. The distance between the two chlorine atoms is 1.98 angstrom, as determined spectroscopically and by electron diffraction. The distance between the two carbon atoms in ethane, the carbon-carbon distance in ethane, I'll change this to ethane, CH3, is 1.54 angstrom. 1.54 angstrom. Now, when we examine carbon tetrachloride by spectroscopic methods or electron diffraction, we find that the carbon-chlorine distance in carbon tetrachloride is 1.76 angstrom. Carbon, 4 bonds to chlorine. I might as well continue to give the example. Well, for this chlorine atom, here again, by forming the bond, chlorine has achieved the argon structure, and the carbon atom has achieved the neon structure. This distance is found to be 1.76 angstrom. 1.76 angstrom, 1.98 angstrom in chlorine, plus 1.54 angstrom in ethane. That is to 3.52. Half of that is 1.76. So the carbon-carbon bond has a length just midway between the lengths of the carbon. The carbon-chlorine bond has a length just midway between the lengths of the carbon-carbon single bond in ethane and the chlorine-chlorine bond in the chlorine molecule. While I'm on the subject, I might mention diamond. Here is a model not built on such a large scale, so small enough so that I'm able to lift it, a model of diamond. Each carbon atom is attached by carbon-carbon single bonds to 4 others that surround it tetrahedrally. And the distance found experimentally between the carbon atoms is 1.54 angstrom, just the distance that is found in ethane and in many other substances in which there are carbon-carbon single bonds. We can understand, too, why diamond is so hard. Here are these chemical bonds, strong bonds, which connect all of the atoms in the crystal together into a single molecule. In order to break a crystal of diamond, as, for example, if you tried to scratch it with some other substance, it would be necessary to carry out a chemical reaction, the reaction of breaking carbon-carbon bonds. This is so hard to do, the bonds are so strong that the substance is very hard, the hardest substance known. I may mention also that the double bond, which is a stronger bond, has length 1.33 angstrom. The triple bond, still stronger, has length 1.20 angstrom. As the bond between the carbon atoms gets stronger, the atoms are pulled more and more closely together. There is one aspect of the carbon atom, the bonds formed by the carbon atom, that I should mention. The question is this: you remember that the orbitals for the carbon atom are the 1s orbital, the 2s orbital, and the 3 2p orbitals. Now, these are the orbitals in the valence shell, and one might well ask, is not one bond formed by the carbon atom different from the other three? The answer to this is a simple one. No, the 4 bonds are equivalent. And we can describe these bonds in terms of 4 equivalent orbitals. Instead of the s orbitals and the p orbitals, we can formulate as hybrid orbitals 4 that are directed toward the 4 corners of a regular tetrahedron, and these orbitals are perfectly satisfactory in providing an explanation of the 4 equivalent tetrahedral bonds. I think that it is interesting that if it happened, as it might well have happened, that chemists discovered quantum theory, wave mechanics, rather than the physicists, then we would be saying that the s orbital and the p orbital that the chemists are interested in are hybrid orbitals formed of the 4 equivalent tetrahedral orbitals of the carbon atom. Let us consider now some substances, some molecules for which the classical valence theory was not satisfactory. An example is benzene. The benzene molecule, C6H6, may be represented, according to classical theory, by this structure, a 6-membered carbon ring. In order that the carbon atoms be quadrivalent, we must have in this 6-membered carbon ring not only the bonds from carbon to hydrogen and carbon to carbon, but also double bonds. But chemists found 100 years ago that if 2 of these hydrogen atoms were replaced by, say, chlorine atoms, one did not obtain 2 substances. A substance in which the chlorine atoms were on carbon atoms held together by a single bond, and another substance in which chlorine atoms were on carbon atoms held together by a double bond. Instead, only one substance could be obtained of this sort. The explanation of this is given by the theory of resonance. This theory states that sometimes, instead of writing a single valence bond structure to represent a molecule, one must write 2 or more valence bond structures and lump them together. Benzene is described now as in being a resonance hybrid of these 2. Those are identical. I'll have to draw the double bonds differently. There's the second one with the chlorine atoms here for dichlorobenzene. We write these 2 Kekulé structures. A single structure of this sort was first written by Kekulé nearly 100 years ago. We write these 2 Kekulé structures and say that the 2 structures together provide a satisfactory description of the benzene molecule. A similar sort of structure can be written for graphite. This represents a portion of the graphite crystal, a very soft substance. The molecule is to be thought of as being infinite in size, a very large layer consisting of hexagonal rings. If I start to represent this structure, I can show carbon atoms attached together in rings. Now, I need to have a double bond on this carbon atom in order that there will be a quadrivalent carbon atom. But the double bond does not need to be here. It may be there or here or here. There are a great many structures that I can draw to represent the molecule of graphite. The physical properties of graphite are nicely explained by this structure. On this scale, the scale of this model, the layers, these giant 2-dimensional molecules, are about this far away from one another and very loosely attached to one another so that they can slide back and forth relative to one another. There are many other substances for which a satisfactory structure cannot be written a single satisfactory structure, and instead two or more structures must be written. Ozone is an example. The ozone molecule consists of 3 oxygen atoms with about a 120-degree angle in this region. If we try to assign a structure in which each of the stable orbitals, too many there, each of the stable orbitals is used in forming a bond or for occupancy by unshared pairs, then we find that this is the best that we can do. Each oxygen atom has now achieved the neon structure, 2 unshared pairs and 2 shared pairs, 3 unshared pairs and 1 shared pair, 1 unshared pair and 3 shared pairs. But this makes this oxygen-oxygen bond different from this, whereas it is known that these oxygen-oxygen bonds are equivalent. The solution to this difficulty is that there is another way of introducing the valence bond in which the single bond and the double bond have changed places. Ozone has a resonating structure. Each of these bonds can be described as being a hybrid of a single bond and a double bond, a bond with about 1.5 bond character. This is a model, a small model, showing the correct packing dimensions of the atoms of sulfur dioxide. The 2 oxygen atoms attached to sulfur, the bond angle again about 120 degrees, and here again there's a double bond and a single bond with resonance between the 2 structures, double bond, single bond, and double bond, single bond. The criticism has been made rather often of the theory of resonance that it is artificial. It is said, for example, that nobody has ever found a benzene, nobody's ever synthesized benzene that has 1 kekulé structure, and that accordingly one should not talk about the first kekulé structure and the second kekulé structure. Now, the fact is that the theory of resonance is no more artificial than ordinary structure theory. It is true that nobody has ever succeeded in bringing into the laboratory a flask full, a beaker full of benzene with the first kekulé structure and another beaker full of benzene with the second kekulé structure. But in fact, nobody has ever succeeded in bringing into the laboratory a beaker full of carbon-carbon single bonds or carbon-carbon double bonds or carbon-hydrogen bonds. And yet, we are happy to talk about the carbon-hydrogen single bond, the carbon-carbon double bond, as structural features of molecules, of the ethylene molecule, the methane molecule, the ethane molecule. In fact, of course, every molecule is something of its own. No 2 molecules are exactly alike. The carbon-carbon distance in one molecule, the average carbon-carbon distance is a little bit different from the average carbon-carbon distance in another molecule. In isobutane, the carbon-carbon distance may differ by a few thousandths of an angstrom from that in ethane. Yet, the approximation of the carbon-carbon distance to the standard value 1.54 is very good for many substances. The carbon-hydrogen distance often has a standard value of about 1.08 angstrom. And we have found it, chemists have found it very useful to talk about structures for molecules that involve the idea of the carbon-carbon single bond, the carbon-carbon double bond, even though these are constructs of the intellect rather than a part of nature that can be completely isolated. Well, in the same way, it is found very useful to talk about the resonance of the ozone molecule between this valence bond structure and this valence bond structure, or to speak of ozone as a hybrid that has a structure that can be represented by 2 different valence bond structures. There is another question that we can answer with use of the theory of resonance, and in answering it, we achieve a great simplification of chemistry, coordination of a great number of facts of inorganic chemistry. I may use hydrogen chloride as an example in discussing this question. What is the structure of hydrogen chloride, HCl? Well, I can write its Lewis structure in this way. There's a bond, a covalent bond between hydrogen and chlorine. Hydrogen has achieved the helium structure, chlorine the argon structure. But of course, if I were giving the talk on ionic valence, I might say I'll write H plus Cl minus. And 30 years ago, there was much argument as to which of these structures, the ionic structure or the covalent structure, was the correct one. Well, we know the answer now. The theoresonance brother can be written for hydrogen chloride, a normal covalent structure similar to the structure in the hydrogen molecule and the structure in the chlorine molecule, intermediate between these structures, and an ionic structure with chlorine negative and hydrogen positive. Well, now we may ask, to what extent do these two structures contribute? And there are several ways of getting an answer to this. In the hydrogen chloride molecule, the distance between the nuclei is 1.27 angstrom. The electric dipole moment of HCl is known. It corresponds to a charge plus 0.2 on hydrogen and minus 0.2 on chlorine. We can say then that there is about 20% ionic character and 80% covalent character to the hydrogen chloride molecule. In fact, it is possible to correlate the amounts of ionic character of molecules containing single bonds with a scale, an electronegativity scale, starting with fluorine 4.0, oxygen 3.5, nitrogen 3.0, carbon 2.5, hydrogen 2.1, boron 2.0, beryllium 1.5, lithium 1.0, chlorine 3.0, sulfur 2.5, bromine 2.8, iodine 2.4, and the amount of partial ionic character depends upon how far apart the elements are in this electronegativity scale. You see, this is a sort of skewed periodic table. Instead, the halogens, instead of lying directly below the one, are skewed over in this way. The most electronegative element is fluorine, the next most electronegative element, oxygen, and so on across. Two elements differ in electronegativity by about 1 unit, chlorine and hydrogen, 0.9. Then there is about 20% partial ionic character. If they differ in electronegativity by about 2 units, the partial ionic character is more than 50%, some 60 or 70%. This electronegativity scale was set up from the consideration that whenever there is resonance between two structures, a substance is stabilized. Benzene is much more stable than an ordinary unsaturated compound involving a double bond. It is the resonance energy between the two Kekulé structures that provides the extra stabilization. Hydrogen chloride is more stable than it would be if it had a normal covalent structure. H2 plus Cl2 forms 2 HCl with the liberation of 2 times 22 kilocalories per mole of energy. The bond, HCl bond, is 22 kilocalories per mole more stable than the average of the HH bond and the Cl-Cl bond. Hydrogen and fluorine, H2 plus F2, form 2HF with 2 times 64 kilocalories per mole. Hydrogen and bromine form 2HBr with 2 times 12. Hydrogen and iodine form 2HI with 2 times 2 kilocalories per mole. Very nearly zero. Now, iodine 2.4 and hydrogen 2.1 have nearly the same electronegativity. Consequently, the HI bond is almost a normal covalent bond, very little partial ionic character, and correspondingly, the bond is hardly any more stable than the average of the bond for a hydrogen molecule and an iodine molecule. Bromine is somewhat more electronegative than hydrogen, 2.8 against 2.1, and the bond is 12 kilocalories per mole more stable. Chlorine is still more electronegative, difference of 0.9. The bond is 22 kilocalories per mole more stable. For fluorine, 64 kilocalories per mole more stable. As a rough approximation, we can say that the partial ionic character of a bond is equal to the amount of extra stability of the bond as given by the heat of formation of the substance in kilocalories per mole. About 2% partial ionic character in HI, 12% in HBr, 22% in HCl, 64% in HF. Now, knowing the electronegativities of elements, we can make predictions about the heats of formation of all substances that involve single bonds. I can take, for example, graphite and hydrogen to form methane. What would be the heat of the reaction? Graphite plus hydrogen form methane. Carbon, 2.5, hydrogen, 2.1. The bond corresponds to about 4/10 difference. I know by comparison with HI and HBr, there will be somewhere around 5 kilocalories per mole extra stability of the hydrogen-carbon bond. And for a methane molecule with 4 of these bonds, then, about 20 kilocalories per mole as the heat of formation of the molecule. There are many other properties of substances that can be discussed in a straightforward way on the basis of the electronegativities of the atoms and the partial ionic character of the bonds. The relation between the energy that is liberated and the difference when a bond between two atoms is formed and the difference in electronegativity of the atoms is the following. The extra energy, resonance energy, due to partial ionic character of a covalent bond is approximately equal to 25 kilocalories per mole. 25 kilocalories per mole times the square of the difference in electronegativities of the two atoms. I can write XA minus XB, where X represents the electronegativity. XA is the electronegativity of atom A, XB the electronegativity of atom B. The difference squared multiplied by 25 kilocalories per mole gives the heat of formation of the bond, and multiplied by 25% gives the partial ionic character of the bond. This explanation of the heats of reactions, all sorts of reactions, applies to substances containing single bonds. One must be careful not to try to apply it to substances involving double bonds or triple bonds because the double bond and the triple bond have characteristic bond energies associated with them. We have talked about ionic bonds and about covalent bonds and about bonds that represent resonance between ionic bonds and covalent bonds, bonds with partial ionic character. This doesn't exhaust modern valence theory. There are still such questions as what is the nature of the bonds that holds together the copper atoms in a copper crystal, where each atom is similarly situated with respect to its 12 neighbors. What about the hydrogen bond? What about oxidation numbers of atoms? Well, it is questions of this sort that we shall come back to in our next lecture.